Your RAG app can pass health checks while its embeddings quietly drift. Evidently helps you catch that quality decay before retrieval gets worse. You'll learn how the pieces fit into a workflow that compares stored and new vectors, then flags drift before answer quality decays. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Embedding drift is a silent failure mode. Your vector store and retriever keep answering, but the geometry that made retrieval work has shifted. The result is worse answers, slower triage, and confused users. Teams add embedding drift detection to get an early warning that the vector space you rely on has changed enough to matter. Evidently is a lightweight library that already knows how to compare distributions, so it plugs into a monitoring pipeline without you rebuilding statistical tests from scratch. What we want is simple: a known good snapshot of embeddings and a fresh snapshot to compare. Then, a tool tells us whether the new snapshot looks statistically different. Picture a reference batch of vectors spread along a line, and a current batch shifted slightly to the right. If that shift is consistent across many dimensions, nearest neighbors can shuffle and answers can degrade. We'll build a tiny pipeline, create a repeatable reference batch, make a current batch that simulates a subtle change, convert those tables into evidently datasets, run a drift report, inspect which embedding components moved most, and run a focus check on those components. The goal is a small automated gate that says "Review this run" before users see worse answers. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we create a minimal reference batch, so we have a stable baseline to compare against. This snippet creates a small, repeatable baseline of embeddings with pandas and np.lid space. When RAG quality decays, you need a stable reference distribution before you can tell whether a new batch moved. The variable ref represents a known good embedding batch, and cols keeps the embedding dimensions explicit instead of hiding them in an opaque vector object. The values are synthetic, but the shape mirrors how Evidently expects embeddings for drift checks. One numeric column per embedding component. The output shows the reference batch size, which matters because every later comparison depends on this baseline. The reference shape works, but a realistic pipeline needs a current batch to compare. Here we simulate what a quiet ingestion or small model change looks like. This example turns the pandas batches into evidently dataset objects with an explicit data definition. The current batch cur simulates a quiet ingestion or embedding model change by shifting MB0 while leaving the table shape intact. That is exactly the uncomfortable case for RAG teams. The app still runs, but retrieval geometry may have changed. Data definition, numerical columns equals cols, tells Evidently to treat each embedding component as a numerical feature, and dataset.fromPandas attaches that schema to both batches. The output shows how many embedding columns are mapped, confirming that Evidently will evaluate the vector distribution rather than unrelated metadata. With both reference and current datasets, we can run Evidently standard drift check and convert the result into a machine-friendly object. This code runs the first real Evidently drift evaluation with report and DataDriftPreset. The important move is passing cur data as current data and ref data as reference data, so the new embedding batch is judged against the known good baseline. DataDriftPreset applies Evidently's drift logic across the mapped numerical columns, which is a practical starting point when you want experiment runs to be comparable. Calling drifteval.dict makes the result pipeline friendly instead of only visual in a notebook. The output shows that the evidently result is available as a Python dict, which matters for tracking and automation. A raw report tells you whether drift exists, but engineers often need a quick pointer to which embedding dimensions moved most. That makes triage faster. This snippet adds a focused debugging view on top of the evidently report by ranking changed embedding dimensions with pandas. A full drift report tells you whether distributions moved, but engineers also need a quick lead on where to inspect first. The shift series compares current and reference means. IDX max selects the most changed column, and watch calls keeps the top 2 dimensions for a narrower follow-up report. This is not a replacement for Evidently's statistical checks. It is a compact triage lens for the same batches. The output shows the largest shifted embedding component and its size, helping you decide where to look next. After you identify suspicious dimensions, rerun a tighter evidently check that watches only those columns and produces a binary gate you can act on. This example turns the exploration into a tiny baseline check using evidently again. Instead of rerunning a broad report only, focus report limits DataDriftPreset to watch calls, the columns that looked most suspicious in the previous step. Setting include tests true adds Evidently's automatic test layer, and compare drift eval, focused eval gives you a side-by-side object for tracking experiment snapshots. The alert variable is a simple local gate based on worst shift, useful for a demo or CI prototype before wiring in a richer policy. The output shows whether this run should be reviewed, which is the small automated signal that helps catch RAG quality decay early. In a real deployment, you would map this toy flow to your nightly embeddings export, run the same sequence, persist the drift dict, and surface any alert to your observability dashboard. That keeps human attention focused on runs that actually need investigation instead of noisy false alarms. This gives you a compact, automated way to detect when your embedding geometry moves. Use it after model updates or on regular production snapshots, so retrieval problems are caught early. One caveat: synthetic or very small batches can be noisy, so favor reasonable batch sizes and repeat the check over time before taking action. For one practical next step, tune the alert threshold you use for worst shift and test it against labeled runs so you control how sensitive the gate is. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.